I turned off the far end so we don't get the phone call.
Oh, yes.
So there's a video conferencing system in here, and
Right.
there's spam video conference calls. So in the middle of talks, the phone will start ringing. It's really frustrating.
Yeah. Actually, our meet.
It's I've had a mixed experience. Sometimes it works, and sometimes it
Yeah.
doesn't. It's hard to.
Yeah.
Depends on the people, the technology.
So we use basically it's over Skype, so that basically we stream it. Anybody can from other end can receive and talk back. So,
Okay.
so it's pretty high quality. So I was very pleased.
Okay. Okay, I'm going to keep this on schedule. The more people are coming, but I'm just going to try.
Hi.
Okay, so it's a pleasure to have with us today distinguished visitor from the University of North Texas, Dr. Krishna Kavi. So, who's actually Dr. Krishna, a person in his, Dr. Kavi, or a person in his organization that reached out to us, informing us of possible engagement with the National Science Foundation Industry University Cooperative Research Center in Netcentric and cloud and software systems. And I was immediately intrigued by many of the details and the vision that you were espousing when we spoke on the phone. And I guess in the conversations that we've had so far today and last night, it's been sort of very exciting, and there's many points of resonance. And I think today he's going to talk about that, as well as I think much of his more fundamental research in
Right.
systems architecture and computer performance.
Right. Okay.
Thank you very much. Welcome.
Thank you. So I'm going to spend maybe about 10 minutes about what IUC-RC really means. So I talked to some people already. Right now, our center is a collaboration with several universities, UT Dallas, Arizona State, SMU, which is also in Dallas, and Missouri. Missouri is dropping out because they could not sustain enough industrial members. But so most of these are taken out of NSF pages, what IUC really means. This program is one of the oldest NSF programs. It's more than 40 years old. So originally started more than 40 years ago, this program. The idea is to establish a relationship or partnership between industry, universities, and government. And each center identifies an area where they're going to focus and help industrial concerns addressing their facilities. So you can read all of the rest of it. We can also have international collaborations. We have some collaboration with the University of Pisa, but you can have. But most of the money NSF money can only be given to U.S. Organizations. So international partners have to bring their own money. So again, all of this is taken out of NSF pages. So NSF gives a small amount of money, primarily to help the administration costs, to running the meetings and my administrative assistant salaries and those kinds of things, and developing the web pages, keeping track of it. Most of the research is done with industrial money. So industries become members by signing a membership agreement and paying a membership fee, and all of the membership fees are pooled together, and then faculty present ideas for research, and industrial members vote on it, and you select projects, and then you conduct the research. Or sometimes industry may come to us and say, we have this problem, we would like you to address it. But again, unlike typical industry projects, these are still basic research. So we will not commit to developing code for them or things like that. We still have to address basic research because that's our mission. So that's what we do. NSF gives a lot of support in terms of what are the rules under which we operate. So for example, one of the concerns many companies have is about IP, who owns the intellectual property. But NSF has guidelines saying that everybody must abide by these rules. So when you join the center, you don't get to negotiate. So you have to follow the standard rules. Same thing with the university. University is restricted to charging indirect cost on these things. So again, you have to play by those rules. And why would anybody want to join? For example, in our center, we have 4 universities. We've been doing more than $1 million per year research in the center, but all members get access to the entire research as a non-exclusive, royalty-free. That means they can't sell it, but they can use it for internal their organization. So one of the things, selling point is, we go to company for your $35,000, $40,000 membership, you have access to $1 million or more research. Some of the centers are even bigger. They are like 6, 7 universities. They have like $2, $3 million per year. But company gets access to, at least looks at what are the research conducted by the center, what are the results, and so on. But if they like something, they can pursue further negotiations to license the technologies. So, and our center receives some awards and stuff like that. And we've been in operation for now 7 years. We have more than, I'll show you some data. So we have 100 projects, more than 20 companies. And many times, papers are actually written with our industrial partners. So again, what's the value for, I assume this is the pointer, yeah. What's the value for the industry and what's the value for the university? And one of the things I didn't realize that when I started this center, but all my students are so excited because they know now whatever they're doing, they're talking to industry, so they know the industry relevance of it, rather than saying, oh, Dr. Kavi asked me to do this, I don't really see any use of this outside of this. So, but they actually appreciate it. They have one-to-one relationship with some industrial mentor. They typically communicate every 2 years. Most of my research in processor architectures. So we work with AMD, Intel, and so on. So we make assumptions about what's feasible. And industry immediately comes back, hey, that's not going to happen. So you need to change your assumptions and so on. So we get that kind of feedback. So the students really love it. So I don't even have to recruit. So many times students come and work for free in the lab because they want to get that kind of interaction. So I was really surprised how valuable that was. And many times they also get jobs with those companies soon after that, graduate. So again, Industrial Advisory Board sometimes define what the research needs are, and so faculty proposes solutions for them, and then IAB votes on those things. So it could either be instigated by the industry, or faculty says that, hey, TI, you should be interested in this research because we have very valuable contribution in this. They make a proposal, and then they vote on it.
Is there a constraint on a research proposal that it has to be done in 6 months or a year or 2?
You can propose task per task, but typically you would like to show some deliverables within 1 year. Otherwise, industry would not have interest. So you can say the first year we'll do this. If it's successful, we'll do second year this. And so you can propose multi-year, but they only guarantee 1 year funding initially. So. Typically, in our case, university does not charge any overhead. So industrial membership, as I said, $35,000 to $40,000 range. Suppose one graduate student, and plus some travel expenses and those kinds of things. So it's dedicated. So then it also tells you the scope of the project. So what can you do with one student? It'll give you an idea of scoping the project. So again, this is more details about our center. Our center says Netcentric, what basically means any networked environment. So we are looking at the actual nodes, processor nodes, the software for the network environments, anything related to those software and systems for network computing, including cloud computing. As I said, I guess I already dropped. Missouri is not even there anymore. Right now it's $35,000 membership. We may raise it next year, but each university has to bring $175,000 in industrial memberships. So if you don't raise $175,000, you will not continue with the center. Any university doesn't bring, so Missouri could not do that. And any center will have to have a minimum of 2 universities to form. And it's not easy to keep membership, so that's one of my job to try to keep recruiting new companies as we lose companies and so on. Just gives you summaries of 2009 to December 2015. We raised almost $4 million in industrial funding, and from NSF, almost 4.7. This is only the center money, so we have other projects outside of the center. And as you notice that we had 50 papers written, co-authored with our industrial members. So they really love that. So we have 6 patents. I think 4 of them are already awarded, and there are 2 pending. More than 150 students and so on. So it gives you what we are able to do this, and this is the selling point for us to go to industry. So here are some of the companies, current companies. As I said, they come and go. Some of them are small companies, SBIR type of small businesses, and some of them actually spun out of our work. So our students went and started some companies, and we lost some big companies. Anytime there's a management change, there's either stock market is going down or something like that, they suddenly say, we're not going to give money to anybody, you know. So that's what happened with Boeing, for example. Just recently they decided that they have to raise their stock prices. The only way they can do is show a lot of cash on hand, so they're not going to give any money to this kinds of things. So I used to have some connections, Oak Ridge. That's why I thought maybe Robert could help us again. But so
I was actually going to ask that question. What was Oak Ridge's interest?
I told you we developed those tools, software tools. Right. Yeah. So, yeah. And Texas Instruments they're still members, but they used to have many more memberships. Some of those groups dropped out. So for example, AMD, Intel, as you probably know, we look at processor development. Armor is a security company, so data security in a network environment. We do that. NXP is Freescale. Freescale is bought over by NXP. And of course, we have telecommunication companies. Sprint, I think Verizon is going to join us soon. Raytheon is a defense contractor, like was Boeing and Lockheed Martin used to be. And there are some smaller companies. This, we try to collect what are the capabilities that we can sort of capture in one slide against all Netcentric things. So we deal with creating optimized web services, quality of service. My primary research is in that red, I highlighted there, new technologies and so on, software for network environment. Everything is centered around network environments. So ASU, Arizona State, does most of the signal processing aspects of it. UT Dallas does software engineering, software testing, and some of the quality of services. We do a lot of security as well as hardware solutions. As I said, to summarize, most of the research in the center is supported by industrial membership, but not only that, once we have a group working together, we can bid for other contracts. For example, a company like Raytheon may bid for a DARPA grant or something like that, and they may say that UNT has some capabilities, we want to add them, so we can work with them to build those. So anyway, so that's a quick overview of what this IUCRC really means. And again, everybody has to follow the same rules, all centers. There's something like 65 total centers in the US, each addressing a different area. For example, there's one which addresses identification, fingerprint, biometrics, and all of those. Most of it is funded by FBI, but so there are, each center identifies an area that they want to focus on. Berkeley has sensors. Technology, Berkeley is actually behind. The center was the one which developed the airbags, for example. So airbags came out of them. So there are a lot of impactful research done by these centers. There's one, I forgot, it was like in North Dakota or something like that, I say, petroleum engineering based. They take pride because the way they came up with a laser detection for the amount of what's petroleum? The levels like 97%. Octane, right? Yeah. So what's the level of octane? In the old days, they had to actually fire an engine and measure it, but they came with this laser technology, so it can actually in real time measure it. That came out of a center. So these are all, because what you're doing is you're looking at areas, there's still basic research, but near-term impact of these. That's only where industry would be interested. So, what I want to talk about now is all my personal research. Some of it is supported through the centers, others are supported by NSF and other agencies. So I have PhD students, masters. I have some really wonderful undergraduate students. David Hash, last night I was telling you, UNT has a program for high school students. We attract high school juniors. They're really sharp, like a perfect SAT score type students. We recruit about like 50 per year. They come and live on UNT full-time residential campus, and they take college level math, science, and physics, and everything. Some of them are interested in computer science, but they come and summertime they have to work on a project. So many of them are like Intel scholars, those kinds of things. But David Hash has perfect SAT score. He's at Carnegie Mellon now, but he came and spent 2 summers with me, and AMD was so impressed they hired him as an intern. This is like 16-year-old kid working at AMD as an intern. So I want to summarize first the various topics we work on, and then pick 2 or 3 of those projects and go into a little bit more details. So we do a lot of memory optimization research. Basically, we develop a lot of software tools so that you can analyze the memory requirements of your application and how your application memory demands lead to cache misses and so on, so that you can optimize. So we have a tool we developed. If there's any interest, I'll go in more detail. We call Lightner. What it does is for each application, it'll tell you which memory access belongs to which data variable, so that you can find out which variables are causing most problems, and then try to reorganize that data. So we also do some hardware solutions for memory. And one of the more recent topic, which is pretty hot and in the computer architecture area, is called processing in memory, or some people call near data computing. The idea is move the computation to the memory rather than bringing memory to the computation. So how does that work? So I'll give a little bit more details about it. We also do a lot of security work, particularly from hardware and systems level. So we don't look at application code development for security or cryptography. So we're going to talk about how do you protect operating system level using hardware and solutions. So this tool is called Lightner. There's a story behind why it's called Lightner, but anyway. So it gives you details about every memory access and relates back to which function called that variable, what's the name of the variable, or if it's an array, what's the index of the array, if it is structure allocated dynamically, which invocation is it, and all of that level details. We also developed a cache simulator. Most universities in computer science use a tool called De Niro cache simulator. That's old, and it doesn't do multicore. So we actually build our own tool, and we call it Moolah. I don't know if anybody realized what De Niro means, right? De Niro is money, right? So cash is money. So my students want to call it Moolah, so we call it Moolah. But it's already used, and some of the DOU work was actually done using this tool. So it's open source. It's available to anybody. Even Lightner is open source. So another interesting research we did on the side. This is not part of the center. This is funded by NSF. In cache memories, when you bring the data, you may have to evict somebody out. So you have to kick somebody out because it's only limited space. If the data is modified, you have to write it back to the memory, right? So it's called write back caches. If we know that the data is never going to be accessed again in the future, why do you have to write back? So I can ignore it, right? So we actually did analysis and shown that many times you can eliminate quite a bit of writes. So you save a lot of energy and so on. But anyway, so this is a side thing we did. So I'm going to go in a little bit more details about some of this new work. Everybody is projecting pretty soon we are going to have the 3-dimensional DRAM memories. Actually, Micron already sells them, but so they're looking at having a DRAM anywhere between 4 gigabytes to 32 gigabytes in one stack of DRAM that you will be able to get it. It's connected through silicon vias, so you have very high bandwidth that you can get, very high, large amounts of data. Once you have this, usually you need to have a logic fabric because you have to have memory controllers and so on. So because DRAMs are all NMOS technology, so you can't integrate CMOS in it. So usually you would like to have a layer of CMOS. You can have memory controllers and so on. But now you're looking at if you have this much area, why not put some processing right there? So you can put some simple processing units. Originally, when this picture was drawn, originally they thought they could stack all of this on top of your multicore processor. Like you have x86 multicore and so on, you can stack all of this. And models show that if you do this, the heat generated by this will heat up your DRAM and ruin DRAM. So that's why now we don't think of doing that. So we're going to put very simple processing units. And for example, the power budget for the processing on this is 5 watts. So you cannot exceed 5 watts for the processing capability. So we have to look at what kind of processing can we embed in those. But in this talk, I'll come to processing and memory a little later, but what I want to talk about is how do we use these memory technologies? So you have 3D DRAMs, you have DDRs, standard DDRs, plus you have non-volatile memories, like flash memories, or PCM. There's a new technology called phase change memories. If you have all of this, can I view all of them together as one big memory? Or do I want to view them as hierarchies, just like caches? So for example, because 3D DRAM is much faster than the other two technologies, maybe we should use that as a cache. Or, as I said, you view everything as a big flat main memory. So we will evaluate both of them. So we can think of whether you want to have a hierarchical or as a flat addressable means everything is on a big address. So with that kind of memory system, you can reach easily several terabytes of main memory on a single processing node. So you can provide that large address space soon. So again, if you're a computer engineer or something like that, you would be interested in finding how do we do memory mapping, page tables, and all of that. So I'm not going to spend time on this, but if you read our papers, we address those also. I'm going to show some results quickly, summarize. Again, papers are posted on my webpage. So we can look at hierarchical where we take the 3D DRAM. I said they can be anywhere between 8 gigabytes to 32 gigabytes. Use that as main memory and your non-volatile memories as disk space. So this is a very standard organization. Or we can look at the 3D DRAM as a cache. So you don't need a SRAM cache, which consumes a lot of power. So what are the trade-offs? Which way you want to use this? And the disadvantage of using 3D DRAM as cache is because it's such a large cache, you need large space for tags. Anytime you build a cache, you need to have tags associated with it. And each cache line will have a tag, and because we're typically last level caches in the processors are maybe 256 megabytes. Now we're talking about gigabytes of cache, so the amount of tag space is really very expensive. So that's the reason why now there's an agreement that you don't want to do this. So we did a lot of simulations. We assumed that you have either 4 or 8 cores unit. We looked at a variety of benchmarks and used open source simulators which allow you to simulate a very detailed execution time, power consumption, and so on. So here is some data to show if you use 3D DRAM as main memory and non-volatile memory as disk space, and you compare that with today's technologies where you have DDR as main memory. So as you can see, for some of the benchmarks, you have quite performance improvement. For example, for MCF is one of the spec benchmarks. Compared to standard organization, we have 66% improvement. Most of it comes from 3D DRAM being faster than DDR. But it also comes from how we organize our TLBs and specialized page table translations and so on. So some of the performance comes from that. So, and this is how many, the performance of the execution. We also have data on cache misses and all of those things too. We also estimated how much extra power is going to be consumed. 3D DRAM is fast, but it also consumes more energy. So you have to validate which one is better. So even though the bars look very large, but the actual scale is not that much. So the difference is not significant, but but also all the extra structures we built, we needed extra tables to maintain our page tables and so on using SRAMs and TLBs. As you notice, that extra hardware doesn't consume as much power compared to the actual DRAM itself, 3D DRAM itself. 3D DRAM consumes a lot of power because of through silicon vias. They are the ones which consume most of the power. If you use 3D DRAM as last level cache, this consumes more energy because we need extra tags. As I said, you need to build tags. And we build the tags using SRAM on the chip because you need to access them fast. However, performance is going to be very fast because most of the data resides in your cache, right? You want to make sure that most of the time data is in the cache. So most of the time, your data is in fastest memory as much as possible. So for the same MCF, now we 100% improvement, twice in the performance. Likewise, we estimated the power and so on. So this, again, how do you use these new memory technologies, what we're looking at? It's not just us, there are several other people studied. Originally, everybody thought, let's do the 3D DRAM as cache. The main advantage of that is PCM or any non-volatile memory have what's called write endurance. That means you can only write so many times, after which the memory is not useful. So flash memory, I think, is like 1 million times or something like that. So you have to throw out your USB stick after that. It's not useful. So using the 3D DRAM as cache, you're minimizing the number of times you're writing. So that's the main advantage of using this way. But after studies, we realized that there are several problems with this because you need a large number of tags. Plus, you're using 8 gigabytes or 32 gigabytes as cache rather than as a memory. So you're wasting your address space. So you're really not increasing your memory capacity, but you're just using it for cache. So that's why we are now moving away from this. We're not looking at this as a real candidate. What's interesting, most recently we have papers just accepted where we said, let's take half of the 3D DRAM as cache, the rest of it is part of the memory. So now we can think of all the combinations of those.
This is obviously very current because you've got the current Intel Xeon fees that
Right.
you have a knob that you turn, I guess, a boot time to
Right.
choose between this.
Right. Yeah. I mean, actually, there are no processor right now with the 3D stack included in it, but I think they're projecting by 2017, sometime second or third quarter 2017, you'll see Intel, AMD selling your
High bandwidth memory on the KNL, I thought that was that.
HBM. HBM is another name for, that's a standard. Yeah, it's a standard for a 3D stack, whereas Micron already sells them, but they call HMC. Both of them 3D stacked memory. So yeah, HBM is high bandwidth memory. So right now they're only Micron is only 4 gigabytes, but they expect it to go to easily 32 gigabytes. and a single stack. And what they're proposing is have like 4 stacks connected to a multi-core processor. So if you think of that in 32 times 4 from the 3D DRAM itself, plus several terabytes from other memories. So we also collected how many, if you use it as a last level cache, how many writes you eliminated to the non-volatile memory and so on. So I just want to give an overview, but if anybody's interested, I'll go in more details, or you can read the papers. So if you just want performance, using 3D DRAM as a last level cache is the best, but it also consumes more energy. But it's also good in terms of minimizing number of writes to the non-volatile memories.
And what size cache line were you using in these models, like page size? Or?
We actually evaluated both typical cache line size, like 64 bytes, but we proposed to using 1024 bytes, but our pages are 32 kilobytes rather than 4K below, because we wanted to minimize the number of page table entries. Right, so, yeah. We felt that 1K byte cache lines are best for this. So the next one is, how do we look at your memory as a flat address space where you have high bandwidth memories? This is the typical picture you will see in many places, where it shows that you have a multi-core processor and you have 4 stacks connected to the processor. Plus, on top of this memory, you would also have standard DDR in addition to that. Could be several, if you want several gigabytes. Then non-volatile memory. So combining this, and these 4 stacks, you can start thinking of terabytes of memory. So with one node, you can have terabytes of main memory. So you can do entire like in-memory databases or something like that. So you don't need Hadoop files. Just load all of that into memory and process it. So the people ask, what's the difference between hierarchical and this? In hierarchical in caches, we have duplicate copies, right? Whatever you have in cache is also in main memory, typically. In flat addressable space, the data is in one of those memories, and you have no replication of it. So one single flat address space. So you'll have tables indicating whether your data is in this stack or in DDR or PCM, and then you have to get them. So what the research is looking at is, since 3D DRAM is the fastest, ideally you would like to keep most frequently used pages there. So what we explore is migrating pages back and forth on meet. So how do we manage when to migrate the pages? Migrate means you have to swap pages back and forth. And what are the energy and execution times involved in migration? Plus, if you're going to migrate something from 3D DRAM back to PCM, then you're doing more writes, right? So you're actually wearing out the PCM. So how do you balance all of these issues? What are the best migration policies and so on? So one of the common things everybody talks about is keeping track of hot pages. It's called hot page policy, basically, saying that you keep track of how many accesses were made to a page. You access a page only if you have a cache miss. If you have a cache miss in last level cache, only then you have to go to DRAM, memory, main memory. So you keep track of how many accesses for a particular page, and once it exceeds some threshold, maybe you say 32 accesses or 64 accesses, then that page is heavily accessed. So we mark that as hot page. And then you decide how many of the hot pages are swapped with cold pages in HBM. So we need to decide how you do that. So do you swap all the hot pages? Then you consume a lot of energy. So we need to come up with the different techniques. This is always a big debate. Most industry doesn't want to change operating systems. They want to use standard operating system even if the hardware changes. The problem with that is most operating systems have to know exactly where the page is. So when you have page table address, you have to say where in different memories you have. And if you transfer the page, you have to go back and modify all those tables. And that itself, it takes a lot of energy. So what we have been proposing, and there's a group in Carnegie Mellon is also pushing for the same, why not build an extra hardware and hide it from the operating system? Operating system shouldn't care where the page is. But that means you have to rewrite some of the aspects of the kernel, so they don't want to do that. So we studied, the impact of page table being modified. And if you modify page table, you have to also nullify all caches, invalidate caches. There's a lot of overhead involved in this. So what we did was we analyzed different policies. There are many more, but these are some simple ones. We want to have baselines that there's no transfers. We don't transfer swap pages at all. Yes? Compiler doesn't change.
Your own compiler,
Yeah.
you're doing it at the runtime.
So typically, if you look at it, what normally you assume is the page addresses are statically assigned. So you're going to say that if it is let's say 8 gigabytes each one, right? From 0 to 8 gigabytes goes into this. Next 8 gigabytes goes into that. Next 8 gigabytes goes into that. Then the address comes here. Once you fill this, then you go to that. So you spread your addresses into all these different devices, right? So here we're talking about terabyte address space. So you're going to say physically we assign addresses to different devices. But what we would like to do is ideally want to make all the all your references to go to this. So if you're accessing a page which is here, and that page is heavily accessed, we want to take that page, move it out here, and swap another page from there to there. But all of this is done in the operating system, but not the compiler. So
like we have typical classical memory optimization, like targeting kind of stuff. So you are not relying on these things
No.
for extracting and
No.
modifying anything.
Right. But as I said, right now we are even relying on operating system to change pages and so on. But ideally, you don't even need to do that. So you have once a big table saying that originally you assume the page is here, but it's actually moved over here. So the hardware can tell you where the page is. So the operating system doesn't even have to do that. So just a translation table. You go there and say, where is the page? Is it in HBM or is it in DDR? And just when you migrate, only change that table.
But would you end up invalidating
It-
things that might live inside the application as well?
No. What you do is invalidate caches. So basically, caches are based on physical addresses. Applications all use virtual address, as you know, right? So you have virtual address being translated into physical address. That's where you have.
You haven't messed with the virtual address.
So that's why the application doesn't change. So application still looks at virtual addresses, and when you actually try to get the memory, that has to be translated into physical address. So caches also use physical address in their cache addressing. So if you change the physical address, the reason why you're changing physical address is operating system says first 8 gigabytes are here, right? If one of the pages moved from there, that means what first 8 gigabytes contains has changed. So the tables have to be modified. And if you modify the tables, previous address here in the first 8 gigabytes is no longer there. So your caches have to be modified. So we wanted to compare with the basic no transfer as a baseline. So we don't migrate at all. What is the performance you get if you don't migrate? Then we use this called hot page policy, just transfer based on some threshold, how many times that page was used. We also came up with some new policies. Many times what we observed is page became hot, so you migrated it. After that, it became cold. So that means it has a large number of access for a very short period of time, and so it became hot during that time, and the basic policy just transferred it. After that, it became cold. So you just wasted it. So what we did was we keep track of, if you transferred it, it was not used next time, its priority will go down next time. So we want to keep track of, is it used after you migrated it? So only those pages which have been shown to be useful in the past will be allowed to migrate in the future. So we also looked at, you should have different thresholds based on the technology, because PCM, non-volatile memory, has very long latencies. So migrating page from there to HBM is going to take a long time. So we need to say that the threshold before that becomes hard, that you moved from slow memory to fast memory, should be different than migrating from DDR or something like that. So we studied different policies. We also wanted to say that at any given time, we will not migrate more than 1,000 pages or 2,000 pages, because migration costs in terms of energy and so on. So there are other types of policies people explored also. So we measured energy and execution times. We also studied limits, saying that what if all of your memory is HBM memory? If you can afford to buy that much HBM fastest memory, that will be the limit, the best performance you can ever get, right? Likewise, you can say everything is non-volatile memory. That will give you the lowest performance. So we can look at all of those. So anyway, here are some results where we show that our policies, particularly the priority, which keeps track of whether it's useful or not, shows that in our policies, most of our memory accesses are going to the fastest memory, which will tell you that is a good thing, right? So most of the accesses go to the fastest HBM and not to the PCM, which indicates that most of the data is in the fastest memory when you needed it. So this NT means no transfer. This is hard policy transfer. This is priority. Then we limit to 4K. And TLB basically means if the entry is already in your TLB, it's a good candidate to migrate and so on. So we have different policies explored. And we also explored, like, in this case, we have 3 memories. We have 3D DRAM or HBM plus DDR plus PCM. Or your organization may only have HBM and PCM, or only HBM and DDR4. So actually, AMD was interested in finding out, can we get rid of DDR completely? So at this today's technology, you don't want to get rid of DDR yet, because PCM is anywhere between 5 to 10 times slower than DDR. But as technology improves, I mean, it's going to be just like maybe 2 times slower than DDR. Then we can get rid of DDR completely.
So when I think of speeds, I must admit, I have sort of at my fingertips the relative bandwidths of these technologies. But what about latency?
Yeah, that's what I'm saying. That right now PCM read latency is between 2 to 5 times slower than DDR, and write is even worse. Write is anywhere between 10 to 15 times slower. So that's why at this time you still would like to have DDR4, which is typically about the same range, maybe 1 time, 1.5 times as slow as HBM. So, and actually that also presents an interesting issue. If DDR4 is almost as fast as HBM, why do you want to migrate at all? Why not just leave them there? So you don't want to migrate them at all. So yes.
So you mentioned about the benchmarks. Are these sequential or they are parallel codes?
These are all parallel codes. We have 8, I mean, some of them are serial, but I'm saying that we have a mixture of both. So, yeah.
And do you use any specific programming model or which specific?
So all of these are multi-core. So basically, most of them are multi-threaded applications. So they're either based on OpenMP primarily. Sometimes we converted OpenCLs to this, but most of them are based on OpenMP. not right now. So we don't want to change compiler level thing, right? So we're only looking at system level. Later on, we can look at how to optimize it. So the way we measure the energy here is we know per transaction power consumed. So we aggregate all of them. We also wanted to measure how many pages were actually transferred. Compared to the simple hot page policy, we transfer fewer pages. So migrate pages. If you migrate fewer pages, it also means that you're consuming less energy because you're not really transferring them. So our policies have been proven to be better than the simple basic policy. Just move any hot page. That's easy to keep track of, but not the best solution. So we actually classified in this one grouping benchmarks which are small. Basically mean the entire footprint, memory footprint is small. So these fit primarily in HBM and maybe some DDR. You don't need that big memory. Whereas large and very large means they exceed the entire memory capacity. And this is more specific data in the actual performance. So it's a relative speed up for each of the benchmarks compared to no transfer. So in some cases, the migration does worse than no transfer at all. So ideally, you don't want to transfer pages at all, if possible. So anytime you transfer takes time, right? You have to copy from one place to another place and consumes energy. So in some of the cases, some of the applications, any transfer is causing more execution time than no transfer. So one of the, what you're talking about is, with this kind of information, what we can indicate in the compiler, change how you're addressing such that most of the pages are always in the fastest memory. So you analyze statically, these pages are going to be likely to be accessed heavily, so put them in HBM to start with, so that you don't need transfers. So once we get this, then we can think of modifying your compiler analysis to allocate pages in the right place. So if anybody's into, we'll give you more details. So most of them are multi-threaded applications. We studied with systems with 3D stacked memory in PCM, 3D stacked memory in DDR4, and all the three together. So.
How sensitive are some of those observations to say choices of page size?
Choice of page size may not impact as much. Because you're still transferring, even if you transferred a single page, is now 32 kilobytes page. That means the amount of data you're transferring is about the same. So this summarizing, if at all possible, don't transfer pages. But if you can somehow come up with analysis to allow you to do that, that's the best solution. But if that is not possible, what you would like to do is come up with some intelligent policy saying that is it going to be useful to transfer the page, or limit how many pages you're going to transfer. And since we have larger access latency, at this time we may not want to eliminate, but pretty soon, if the PCM reaches about the same access latency, in this case is that can be as slow as 4 times. Once the PCM technology comes to the case where the latency is only about 4 times as DDR, we can get rid of DDR completely. So one of the most recent paper we submitted and was accepted was, can we use both hierarchical and flat address space? So we use half of, not half, but a portion of HBM as a cache. Rest of it is a main memory, and we transfer pages. So we've shown that that is actually the best solution. I didn't include any data because the paper was not accepted yet, and my co-authors would want to wait until, I don't know if you know, in computer science engineering now, our conference papers are valued more than our journal papers in our computer science. And some of the conference papers have called double-blind review. Reviewers don't know who we are, authors, and we don't know who the reviewers are. Plus, in the last 4 or 5 years, we as authors are given to rebut reviewer comments. So they actually publish comments before final decision is made, and you get to answer any of the reviewer comments, and only after all of that the paper is accepted. So until that time, we would like to keep our identity secret, so that nobody knows who we are. So processing in memory, I already motivated why this is feasible. This idea is really not new. People have been exploring this for almost like 20, 25 years. Why there is a lot of interest now is now technology makes it feasible, because back in around 90s and 2000s, we did studies, and Berkeley has a thing called IRAM, Intelligent Random Access Memories, where they moved some processing into the memory. But again, as I said, you can't mix NMOS technology with CMOS. Any processing has to be CMOS. So they couldn't really manufacture them together. But now with the 3D stacked memory, you can have one layer of CMOS. You don't have to mix them at all. So there's a lot of interest nowadays to do this. So of course, there are some other reasons why. There are many applications which are like streaming. They don't benefit from caches at all. So because cache is useful if you're going to reuse the data many times. So you want to bring it to an area where you reuse it, called localities or whatever. But many applications don't have those. You just keep bringing data, new data, and process it and get it out. So using large caches really not beneficial, and caches consume a lot of power. So that's why there's also saying that, can we eliminate caches? If we eliminate caches, how do we get large bandwidths and so on? So we can migrate them from processing in memory. But of course, there are so many choices in architecture. What architecture do you want to put in the processing in memory? What computation do you want to migrate? And so on. That's what everybody is studying now. And how do we modify the operating system? Or do we want to modify the operating system? And so many others. Synchronization between processing in memory work and the CPU work. If they both access the same memory at the same time, what happens? So all of these things you have to look into. So again, the same idea we're talking about. You have a multi-core processor. Everybody talks about 4 stacks for, I don't know why, for some reason that's the standard now, everybody. So each stack of memory would have some processing in memory capability. Here, by the way, this is the Micron. So actually you can get, today, Micron's HMC stack if you want. They worked with Intel, and they're selling all of these. That's why I was following Micron's stock more than doubled in the last 6 months. What we want to do is come up with a completely new way of thinking of computation. And we want to use reconfigurable computation. We don't want FPGAs. We will use something called coarse-grained logic. So our architecture would look something like this. This is the block diagram approach. This AMM is nothing but advanced memory. Those are the 3D stacks with the processing in memory. You have multi-core processor with its own L1, L2, and L3 caches. But each one of these processing in memory would have logic divided into 4 quadrants. So each quadrant would contain something like this. It has a small amount of local memory. It's called scratchpad memory. And we have large number of FPGA, not FPGA, but coarse-grained reconfigurable logic. I'll show you how that works. And then we would have a simple controller which manages communication between the host and the processing in memory. So what we mean by coarse-grained processing is we will start with ASIC versions of some standard functional units. ALU, sequences, they're all fabricated. and there is interconnection between network between these units. So in order to create a computation graph, we first draw a computation graph and say how many ALUs you need and so on, and then connect those ALUs, say that the input of one ALU comes from some other ALU, so you basically wire them up to create a computation graph. Once you do that, there's no additional instructions, no additional computation defined other than just the graph itself. They're sometimes called data flow graphs. Here is an example. Here is FFT. So my student did it by hand, this one, optimized version, but we can generate it automatically. So as you can see, all you have is floating point adders, multipliers, and so on here throughout this. And using those coarse grained logic unit, we're going to say that I'm going to program one of the ALUs to do subtraction, another one to do multiplication. Configure that. So once it's configured, it only does subtraction, nothing else. It only does multiplication here. And then connecting interconnection, saying that this subtractor is going to feed data to these. And basically now what you have is you give the input at the top, like a pipeline, the data goes down from one unit to another unit and it generates outputs. And you can pipeline keep feeding the data in the front like streaming, so you get computations done. So once the pipeline is full, you get one result every cycle. Bigger computation means bigger graph, but once you fill the pipeline, you get one output every cycle. So, and as you probably can guess, how many instructions are needed to, if you look at the x86 code, it's probably about 2 pages long, this code for the same thing. And you have to fetch one instruction at a time, decode it, and execute it. All of that is eliminated by this. These devices are going to be slower than x86 because we don't want to consume power. So, as I said, there's a 5-watt limit on what all of these units together can be. So they're going to be slower. So you may not achieve the performance gains, but energy savings are tremendous. So for example, our models, we did many applications. We are actually extending. We have simulators now, so we can automatically generate a lot more data. To give you an example, using MapReduce, histogram, word count, and so on. So we only took kernels, not the entire application. We found out how many execution times. If you execute that on x86, how many microseconds it takes. If using our architecture, we call dataflow processing in memory. DFPIM is nothing but dataflow PIM. We show that like 5.5 times speed up for the whatever data we process for that. I don't remember on top of my head. But look at the energy savings. So we consume only 0.7% of the energy needed by the x86 implementations. And that's pretty consistent. Very large. The main reason for that is once you configure the graph, there's no other additional energy consumed other than data going from one unit to the other unit. What we want to look at now is given an area, a specific area, how many of these ALUs can we build and so on. And I was talking to Robert the other day. What we want to do is, if you talk about, can we get a lot of data at the very beginning, just keep pumping it through this. And maybe construct 4 of these if you want, and keep pumping the data, so you get 4 results every cycle, and so on. And we want to find out how many of these can be placed on the silicon area within 5-watt budget. Those are the things we want to look at. So, what we also wanted to do is, if that FFT is hand-drawn, right? If you have source code, you can have a compiler generate those data flow graphs. What if you don't have source code? Can we take executable, reverse compile, and create those graphs? Anytime you do that, your graphs are not going to be as efficient because compiler generates a lot of junk. A lot of intermediate results stored in registers and those kinds of things. So if you don't have the source code, your data flow graphs are not going to be as effective, as efficient. So we generated these automatically, reverse compiling, So our speed ups is only 1.22 rather than 5 times for benchmarks, but we still save energy. So we are actually now trying to build tools to automatically do reverse compile. What we do is that we analyze profile applications, say this portion of the code is heavily accessed. So we take that piece of the executable, reverse compile it, generate data flow graph for that. Yes?
Just a question, like when I saw your data flow graph, are you thinking of like deep learning applications?
Could be, yeah. Whatever it is, yeah. Yeah, can be any kind of application. So we actually even analyzing now some of the Department of Energy proxy in applications, which are nothing but kernels from the chemistry, computational chemistry, and so on. So they don't want to disclose everything, so they created an application somewhat similar to chemistry computations. So that's what they call proxy applications. So that's what people are looking at. But we want to analyze big data applications, machine learning applications. So I don't know if there are deep learning benchmarks yet. So if they are available, we'll be glad to look at them. So
on your CGRL, you can only get a snippet of full FFT graph. So do you have a larger level architecture that connects multiple chips together?
Yeah, because you still have the host. Host is going to coordinate. Like, so for example, there are 4 quadrants, right? That means you can actually get 4 FFT graphs, right? And there are 4 stacks. So you can get 16 of them computing. So. We also did, what we did was, instead of our data flow graphs, what if you have a simple ARM course rather than our data flow graphs? Because data flow graphs programming, unless it's automated, you have to draw those graphs yourself and so on. Suppose you just simply have ARM cores. We studied and looked at, you can embed actually about 25 to 32 simple ARM cores in that silicon area within the 5-watt budget. And our ARM cores have only L1 cache, nothing else. You don't need that much any cache because memory is right on top of you. So why do you need those? So we estimated in logic area how much you can get. As I said, we only have L1 cache, nothing else. And the frequency, maximum frequency we want to operate those ARM cores is 1 gigahertz. Most of the time we want to run them at 600 megahertz to save energy. So we did this study also. And again, we looked at if you use ARM cores for word count, histograms, how much performance gains you're going to get. Here, you're not getting as much performance gain because all we did was we only did word count. The only map portion is sent to the PIM. Reduce is done by the host. So in the simple case, that's what we did. So you have to still communicating with the host. There's some performance loss. So initially, this was a 2 years old paper. This is an earlier version. But we still have saved some improved performance. But we also wanted to look at bandwidth consumption. If you put those 16 ARM cores on the multicore processor and keep sending the data to the processor cores, how much bandwidth is consumed for these applications? As you can see, there are a few times you consume like 12 gigabytes. But if you actually move those ARM cores onto the PIM, you consume much more bandwidth. And that bandwidth is available. Why not use it? And in order to use that much bandwidth, we estimated you needed 64 ARM cores. So if you want to consume as much bandwidth as 16 ARM cores placed on the processing in memory, you need 64 ARM cores on chip. But to transfer that much data, HMC Micron has 4 links. Each link can transmit, I think, 40 gigabytes. Yeah, each link can transfer 40 gigabytes, and each one consumes 5 watts of power. to get this 88 gigabytes, you need 3 of them, or you need 15 watts power. As I said, we were allowed only 5 watt power. So basically, we wanted to look at different architectures. I'm going to show this data, but it just should stay in this room because it's not accepted yet, this paper. But we also, what we did was, let me show you. What we looked at using GPUs as PIM cores. So we studied dataflow as PIM cores, ARM as PIM cores, as GPUs as PIM cores. So in this study with AMD, what we talked about is it better to use GPUs with the CPU, like AMD Fusion cores or Intel, cores where they combine x86 along with a GPU, all on the same chip, or if you have PIMs with GPU, is it better to compute there or here? When do you make a decision between those two? The GPUs that sit up with the CPU are high performance. They can run with up to 3 gigahertz, whereas those GPUs sitting under the memory have to be low power. So they cannot be run at the same frequency. So you don't get as much performance, but you have a lot of bandwidth, right? So if your application is bandwidth bound, then you want to send it to the processing in memory. The application compute bound, you don't need as much bandwidth, you should execute it on the main CPU. So we did studies like that. So what we did was, as you can see, many of them applications, several of them are proxy apps. Analyze each and every single application, not just application level, but each kernel level. For each kernel, we decided what is the optimum placement. Should that kernel run on PIM or run on host? Both to improve performance as well as power. So this is the power optimum solution. As you will notice, power optimum solution usually means it's best to run on the PIM. So this blue bar is the optimum solution. And as you can see, if you run the kernels on the PIM, they give you the lowest power. Whereas if you run it on the host, it consumes quite a bit more power. And we did a lot of other analysis saying that which one is more important? Is energy more important? Power is more important? Or you can say, I want to say energy really important, so I can say energy square. So I can say, usually people talk about energy delay product. So we can say energy delay, ED square. So we can come up with different ways of optimization, which one is best. So again, we looked at it. But what I wanted to do, I just skipped this, but what I wanted to talk about is, I already talked to Robert, we are very much interested in collaborations. So what I would proposed is a very large framework where people can contribute to this with their own ideas for architectures, memories, and so on. And then we will analyze lots of application domains, kernels, and identify which is the best architectural environment for each one of those. So any new application, all we have to do is run it on one and say, this application looks like one we already saw. So using machine learning. So we can indicate what would be the best architecture for them. And this allows people to do compiler optimization then. Anything, the framework is built so we can study whatever. If I have a new idea, small new idea, I just plug in my new idea and evaluate in general environment rather than building the whole thing yourself.
Thank you very much. Actually, I had a quick question about in the PIM space. I mean, your processor is near one piece of memory, but quite distant from other pieces. So
right.
One of your benchmark kernels was
yeah.
the matrix multiplier.
Right.
And that's an example where essentially every row has to touch every column.
Right.
So how do you navigate bringing data together?
Basically, I think some of those already do that where you tile it and stuff like that. So some of the kernels we looked at, they're already tiled. So we don't, so you do small
so
kind.
Looking at a single tile rather
Right.
than the whole thing. But you've still got to do the full thing. So
Right.
you have to do sort of data motion to prepare to do the PIM.
Right. So some of that would be done in the host. So that's where you separate where it should be done and so on. So again, each application has to be optimized. So yeah.
Do you have any thoughts on ideas on how deep memory hierarchies will interact with interconnects?
These kinds of things, or these kind of deep memories. You look.
The fact that you've got these different places where you put data, and then you're moving data in and out of a particular machine on
Right.
or whatever.
Right.
How will that?
The interconnection between the nodes or interconnection from the node to outside. Okay, so that does not have to be changed at all, because this operating system will still have to get the data into a buffer, network buffer, and send it out. So it's up to the operating system to bring the data into the buffer no matter where it is. So the network operations themselves don't change anything. So. Yeah. Right. Right. So.
It's not just you've got to take it out and bring it back in again, but sometimes
That's still the case today, right? You still have last level caches, that you have to handle that. So I don't really see, if you are going to use HBM as a cache, right? So there's no difference between that being a cache today versus today's last level caches in the hierarchy. If you use HBM as a flat memory, it's as if it's just one big memory. Whether you have DDR memory or these memories, the system has to bring the data from one of those units into buffers, so that the buffers are typically sit in your HBM memories, and that's where you connect to the network. So I don't think there's a significant difference between whether you have this kind of technology or whether you want to use HBM as a cache. You still have the same problem today with your last level cache. So I don't know, maybe I don't understand the problem, but
the memory hierarchies are getting deeper in the system. So you have more possibilities of where to put the data. So then you will organize what goes in which direction more.
right. But I think that's the reason why, as I said, there is a general feeling that you don't want to increase the number of levels in hierarchy. So,
I agree with you, but for the systems we're getting, that's what they have.
I don't know if there's an HBM cache yet. You have an L1, L2, and last level cache typically.
No, in the Intel system, right? So there's the high bandwidth memory next to the Xeon tree. I think as you were indicating, they basically got 4 small stacks.
Right.
And one configuration is cache.
Right.
SSH2 cache is the entirety is cache.
Right. Right, right. Yeah, again, I'm saying that you have the same, on top of that, you have LLC, last level cache? I don't think. You do? I don't know, yeah.
Well, it's between the, in that case, it's between the HBM is in between the regular cache and the DDR memory.
Right.
Not the
PCM, yeah.
PCM.
Yeah.
Right, yeah.
It's quite a variety.
Yeah, yeah, yeah.
Yeah, and the whole Newman technology plays into it as well, because
Right.
the performance is very sensitive to the layout of the computation. And at that point, yeah, we do need the compiler and
That's
everything.
right. But if you can automatically learn and transfer pages, you don't have to burden, the application. So
everyone else ran off obviously because we were like studying out that. So no, I'm going to finish the seminar and then you can ask your questions. So thank you very much.
thank you.
Okay, now you can ask.
So I saw the term dynamic voltage frequency scaling. Is it your next step to?
No, we actually did. So for example, for the AMD work, what we did was you have GPUs sitting on PIMs, GPU sitting on APU, like in this processing course. We also wanted to control the DVFS state for each of the kernels. So what would be the best DVFS state for each kernel? So we analyzed that too. To say if your goal is performance, what will be the DVFS state for that? If goal is low energy, what will be the DVFS for that? So we analyze those.
So one Like, have you heard of this? Maybe I think definitely over provisioning, power over provisioning. So how over provisioning? Do you think that can fit with this thing? Like,
there's a standard agreement that the processing in memory, if you, the logic layer and 3D stack cannot exceed 10 watts, period. So part of it is reserved for memory controllers and stuff like that. So general assumption is no more than 50%. So like 5 watt is basically the limit.
okay.
So like ours, we included, estimated if you included 16 ARM cores, it comes to much less than 5 watts. So you can probably put more of them. So if you want, so you can't really over provision there because you had limited by 5 watts max.
Because what I meant by over provisioning the hardware, like you increase the number of nodes. So at the same time, you decrease the frequency. So at the end, the throughput, the performance,
Right.
it doesn't change.
Right. We studied that, saying that if you have 32 cores, right, and you only use 16 of them at high frequency, or 32 at low frequency, DVFS. Yeah, we did study those,
Okay.
but we are still limited to total FI in watts. How are you going to do that? So you had to account for leakage and all of those things. So you don't want to put too many of them because of the leakage, you know. So yeah. So.
I've been pushing it and
Thank you.